Dear students, I hope you are doing well. I think I have succeeded in giving you feeling of how various bands, absorption bands, they come in absorption spectra of metal complexes. For example, in lecture 6, we learned how the 5D orbitals, they split up. You know very well now by now that they split into T2G and EG. And if there is, let's say, one electron, it will stay first of all here in T2G set, and then when it gets some energy, which is represented here, it will go up here. This absorption is reflected into the absorption band. In lecture 7, we went a step forward and we learned about Jahn-Teller effect. There was an observation that instead of getting the one absorption band, there is a shoulder in there. And Jahn-Teller effect very clearly explained why the shoulder should come. And I think I don't need to repeat the statement of Jahn-Teller. If there are unequally occupied orbitals, then they always go into a configuration or symmetry which is more stable. And as a result of this Jahn-Teller effect, instead of getting a pure one band, we get a shoulder with the, it is very well explained. Okay, D1 was a very simple system, reason being only one electron. But when we will be dealing with 2 electrons, 3 electrons, 4 electrons in this system, there will happen what? Inter-electronic repulsions. The 2 electrons, they will repel each other. And if they repel each other, something different should happen. What happens? Okay, we will now discuss that in D2 ion spectra in good details, in which this inter-electronic repulsion will play its part, and we will see how it and what it does. I'm just quoting 2-3 examples of D2 system: titanium and its salts, or titanium and its complexes, vanadium complexes, configuration. You know very well, I have written here, when it combines with some ligand, maybe ammonia, water, cyanide, ethylene diamine, or whatnot, then it forms a complex. I'm showing it here, and this complex looks like this. It's given in the diagram. The ligands are approaching right on the axis. See this, x-axis, y-axis, and z-axis. And now we have 2 electrons. These 2 electrons, as a result of these ligands, okay, this 5D orbital split T2G, EG, 2 electrons will be here. Now, the ground state configuration here should be called T2G2. That is 2 electrons in T2G set. Okay, supposing 1 electron goes up from here, it goes up there. So 1 electron is here now, the other electron is here. So now the configuration will be T2G1 and EG1. Okay, 1 electron up and the other electron down in EG. This gives rise to the following terms. Now please note, due to inter-electronic repulsion, this T2G, we will consider T2G multiplied, but this is dot multiplication. It gives these one, okay? You will learn it in group theory later on, but these are the, again, Okay, group theoretical terms. These are energy states. A1 energy state, E energy, T, and all. Okay, these are given. This product is given on page 41 of ABP लीवर की बुक में ये वहाँ पे दिया हुआ है. Okay, similarly we can have this configuration. Okay, one electron in Eg and one electron in T2G. When these are multiplied, okay, group theory helps us multiplying it. We get these one. Okay, and supposing if the both electrons go up, okay, when we give them more energy, then the two electrons come in the Eg. Naturally, then the configuration will be Eg2. And Eg2 means Eg multiplied by Eg. Well, this you can see in your book. Okay? Since I'm not going to teach you group theory, I will, but not in that detail. But then I think you should know about it. Okay, these terms, energy states, they come as a result of product of these two. And this is what it is. So, and if electrons did not repel one another, then each of these states, Eg2 or T2G2 or T2G1 and Eg1, they will remain the same. Nothing will happen to they will not split up into these things. Okay, we know very well about the triply degenerate p orbitals. These are p orbitals which I am showing, px, py, and pz. You are familiar with them. Now, what I'm saying is T2G. What is it? T is triply degenerate. This is also a set of three, okay, states. Three degenerate states. 1, 2, and 3. Now please see, I have put it here like this. P1. You know very well how to calculate the microstates. 6. Or P2, I have explained in the classroom, will give 15. And you can do it yourself. Similarly, T1 will give 6. T2T will give 15 microstate. Same thing. The fact that multi-electron system electrons do repel one another, it simply means that this T2G configuration, which contains 15 arrangements, 15 microstates, it splits up. As a result of interelectronic splits up in octahedral environment and give rise to this. These are 4 energy levels, 4 energy states, 4 energy terms, whatever. Please note it, we call these one E, T, A, B as group theoretical terms, group theoretical energy terms. Okay, similarly this one gives, and similarly this, if you add them up, it comes out to be 11 states, energy state. Very complicated, okay, in octahedral field. And it may result naturally. It should not give one absorption band, may give 3 bands, 4, 5, 6, 7, whatever. So we do not know, but later on we will be able to tell how many bands it will give. And this is what we call as absorption spectroscopy. Now, with this, what I have explained, I can simply say that simple crystal field theory, which simply gives the idea of T2G, and well, this cannot explain spectra of multi-electron system. Okay, so diagrams depicting the relative energies of various terms. That means term triangular are required. This will be discussed in the following pages. Now, let's see. D orbital simple. Okay, I don't need to. When, okay, the electrons, two electrons are put in a weak field. Weak field means weak ligand field. Okay, and one electron can easily go to T2G from to EG to give this configuration. You see that if this delta is small, okay, if delta is small, then we require only small energy. So T2G electron, one electron can easily go EG. And even the second electron will go here and will give you this combination. In a weak field, splitting delta octahedral is very small or close to no field or zero field, or I have just put the language of the book, just small perturbation, ऐसे थोड़ी सी इनको हरकत होती है. In such cases, free ion titanium 3, which is a D1 system, okay, D2 may be considered as free ion terms. When there is a very weak field or no field, then you know very well D1 gives terms, D2 also gives terms, okay, and free ion gave what? This, okay, terms. Good so far. So there will be, we will discuss with you weak field approach. When there is a very weak field, we get these terms. D1 gives a doublet D, and D2 gives triplet F, triplet P, D, singlet D, G, S, and all that. If the free ion is now placed, okay, this is the free ion. These are free ion terms. If you take these terms or the free ion and put it in the octahedral field, what happens to these? This is very simple. Whatever happens to p orbital, same thing happens to this state. What happens to d orbital, same happens to this. And similarly, whatever happens to f orbitals, same happens to this. You will understand that more in a minute. So D, see this one, I have written D term in octahedral field gives doublet EG, doublet this, T to G. Okay, and if you add them up, it will come to, it should come to 5. Okay, D2 terms in D4H square planar, okay, will give these group theoretical terms. Note, splitting up of a term state is independent of this spin. Okay, it doesn't say, splitting doesn't do anything with spin. This 3 doesn't become 4 or 2 as a result of splitting. It stays the same. D splits into this, 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 and this with triplet, 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 triplet. Now please see this. This is one-dimensional. One. This is also one-dimensional. This is also one-dimensional. 1, 1, 1, 3. This is 2-dimensional. 4 and 5. D you know very well. Orbital degeneracy is 5. So it will, if you count down, it will come to 5. I have written here. E is 2. T to G is 3. Triply degenerate. Doubly degenerate. F is 7. Orbital degeneracy. This is 1, 3, and 3, 7.